All right, so we're starting into air friction now. Now, air friction is based upon velocity. The force of drag is what we use. And by the way, this air friction idea can also be applied to any force of drag or friction that is based upon how fast you are going. But it increases as your velocity increases. So if you will, I'm going to start sliding this. Force of drag is going to equal negative BV. Now, B is the drag coefficient. If we're dealing with air friction, that's actually talking about how thick the fluid is, the density of the fluid that the stuff's moving through. The most common fluid that you'll deal with is going to be our atmosphere, but this works for any fluid, right? The same equations, just your B would change for density of fluid or for how sticky the fluid is. Also, that accounts for surface area of the object that's falling and all the different other ideas that we need with aerodynamics of that thing that's falling. That's all absorbed into one constant, B. So negative B times the velocity V. Now, why the negative sign? Because whichever way your velocity is going, the force is always going the opposite way. That's the idea with friction too. Force of friction equals negative mu times normal force, because friction always resists the direction of motion. Now, this only works for small objects and generally low speeds. You have linear drag. As it gets more complex, or as you go faster, or you have larger objects, then you actually need negative C. C is just a constant out in front, but notice now what happens to the velocity, V squared. And if we're even bigger or even faster, maybe you have to get up to minus D, another coefficient, another constant that takes into account all the things about the fluid you're going through and the object that's moving, times V cubed, so forth, so on, and it continues depending on how fast you're going. Now, one of the neat things whenever you're modeling this, let's say we are a little bit larger and we're going a pretty high speed, and so we need this negative CV squared. Well, V squared here is going to make this entire term so much larger that we don't even need the negative BV anymore. In fact, this adds very little to the actual drag force whenever this part is needed, whenever you start going fast. So you could actually completely drop that off. That's why whenever, and I'm just going to cover this stuff back up right here, that's why we don't even worry about the combination of all of them. Whenever we talk about linear drag, we're going to talk about small objects, slow speeds, force of drag, negative BV. And then whenever we get to quadratic drag, aka a little bit larger objects, higher speed, force of drag is going to equal negative C V squared. Now the question always comes up, how do I know which one it is? Well, I'm going to tell you which one it is, or the AP exam will tell you which one it is. Otherwise, you would have to approximate it. And we would need to find this out experimentally. We might do an experiment this year where you actually need to decide which model is better for an object that is falling. And we'll talk about that later on. Now, drag, it always resists the direction of motion. So look over here at this free body diagram thing going on. Whenever it's initially at rest, you have mg, force of gravity, pulling down, right? And so it's going to accelerate it down. But as it picks up speed, drag in force increases. So it slows the acceleration down. Here it should be the acceleration should be 9.81 if we're calling down positive. But now the acceleration isn't as large because part of my gravity force is balanced out by drag force. As I continue to fall, though, my velocity finally gets so large that the drag force completely balances out mg. Notice how now the drag force, the magnitude of that vector, is completely equal to the magnitude of your force vector. By the way, I don't like the fact that these vectors aren't actually touching the object. For some odd reason, AP actually tends to sometimes take off on your free body diagrams if you don't put the vectors, the force vectors actually attached to the dot or to the object that you're drawing your free body diagram on. Now, terminal velocity is the maximum speed an object falls due to air resistance. In other words, drag eventually slows it down. This is when the force of gravity and drag balancing out, causing it to fall, key here, at constant velocity. If we were to graph this out over here on a velocity time graph, your velocity is increasing in a linear manner. Remember, the slope of a velocity time graph is the acceleration, and the slope right down here should be 9.81 if I'm calling down positive. But what happens is now drag kicks in, and as the velocity increases, the acceleration decreases. Notice how the slope is starting to level off, and it continues to level off until you start to get to the terminal velocity. And so this asymptote, if you will, is the terminal velocity where whenever you approach the terminal velocity, you're not going to go any faster. The forces are actually balanced out. Now do remember, this idea works with both with both drag, I should say, in the x-axis, where it's whatever form of friction or drag is the only thing acting. There's nothing accelerating it. It's in the x-axis, but it also works in the y-axis, and that's where we're kind of focusing things in free fall here. Now let's solve one problem specifically aimed at that terminal velocity. Let's solve for it. What's the terminal velocity of an object in free fall that experiences linear air drag? And I'm going to solve this in pure letter format, not numbers. We could insert numbers in at the very end where we say, okay, here's the object's mass, we know the acceleration of gravity is 9.81. Let me give you the drag constant b. Now substitute it in and solve. But that's really easy. Let's just go ahead and let's work it all through in letters. So I have a free body diagram over here, and I'm going to call down positive and up negative. It doesn't matter. You get to choose. I just generally choose for this kind of problem, the direction that we're actually moving down to be positive. Doesn't matter as long as you're consistent. Drag going back up negative. And notice the magnitudes here, the length of my arrows. They are equal in length because at terminal velocity, the force of gravity is completely balanced out by the drag force. We are going so fast that the two forces are now balanced out. So I have some of the forces, right? And this is all happening in the y-axis here, right? And I am, then sum up my forces. I have positive force of gravity minus the force of drag. And I know the equations for force of gravity and linear air drag. So I insert those two equations in, right? Force of gravity is mass times gravity, linear air drag, so we're not going too fast right now, or the object is small enough to where even though we're picking up speed, it's okay. Negative BV. Notice I didn't negative the negative. I dealt with direction with this negative. I said, hey, drag is negative, right? So negative drag, and I didn't then put minus negative BV. That doesn't make any sense. The idea here is I want this to be going the opposite direction, the drag, the opposite direction from the force of gravity. And if I made it negative, negative, a negative times a negative is a positive. So if I did minus a negative, then it would switch around and drag would have been going down with gravity. And that's not what I want. So I already dealt with direction by that negative out here, so I don't need to double deal with direction. All right, now I do know something else about this problem. At terminal velocity, we are going at a constant speed. We can't go any faster. So that means the acceleration is 0, leaving me mg minus bv equals 0. Then I can add that BV simply over to the other side. I'm trying to find the terminal velocity, and I probably should change my notation here. I'll make this VT now. Reason for that is whenever the acceleration is 0, this part right here, right, whenever acceleration becomes 0, I'm saying, hey, we're at terminal velocity. We're going at a constant speed. The two forces are completely balanced out. And I'm trying to solve for what the terminal velocity is. Divide both sides by b, and now I have mg divided by b is going to be the terminal velocity. So if I'm given a mass of an object experiencing linear drag and the drag coefficient b, m times 9.81 divided by that coefficient will give me the terminal velocity. This is a proof that you need to be able to do for the AP exam. Now that we've solved for the terminal velocity, let's actually find an equation that describes how the velocity of an object that's experiencing linear drag depends upon time. So in other words, I'm trying to solve for the velocity or the equation of this curve right here. How does, as my velocity increases, what happens to it? Well, it doesn't continue to increase at the same rate. It starts to curve off. So at any point in time, t, how fast are we going? This is going to require a little bit of differential equations, something that we've actually already done in our class. So I draw a free body diagram, knowing that as time passes, the force of drag is going to increase, right? So this Fd would actually increase. I'm choosing down positive, up negative. Sum of my forces, Fg minus Fd equals ma again. Now we can substitute in what Fg and Fd is. So once again, I'm using linear drag instead of quadratic drag, so I'm using negative BV, not negative CV squared. So I insert that in, and I can't make this A 0 because I'm not at the terminal velocity here. I'm asking for the entire picture, for everywhere on this graph. I want to know this equation right here of the entire thing. So it is still accelerating at parts, so the acceleration is not 0. I have to leave it as A. In fact, it's constantly changing depending on what the time it's at or what velocity it's at that point in time. time. And I want to figure out how velocity depends upon time. So now let's set up our differential equation. Remember that the entire trick behind this, A is the same thing as dv over t. So all I have to do is change A into the derivative of velocity according to time, dv divided by t, divided by dt. This is the differential equation here. And by the way, just simply getting to this point in this problem, going through the free body diagram and solving down to this point, is worth a decent number of points on the AP exam. Now let's actually solve for velocity. That requires the separation of variables. I'm going to start out by just dividing both sides by mass. Whenever I divide both sides by mass, I end up with g minus b, and let's actually work this through a little bit more here. That means I can split this up. Notice over here, I have in the numerator something minus something, and then one thing in the denominator. That's the same thing as mg over m minus bv over m equals, now these m's would cancel out. Now I've just got dv dt. I'm trying to get rid of that m that was on that right-hand side because it's kind of in my way for me to separate my variables like we did. Notice these m's also cancel right here. So now I'm just down to g minus, and I'm going to pull this v out, b over m v equals dv dt. Okay. This is the exact same concept also. Basically, 1 over v, imagine this v divided by 1. So b over m times v over 1 gives me this. So I can pull that v out and make it multiplied there because it was in the numerator. Now I'm ready to separate my variables. I'm going to have to move this entire thing over underneath the dv and this dt over to the other side. I don't have any other t's, but let's start out with that. Let's multiply both sides by dt. So let's get it over here. Now I got dt times g minus b over m v equals dv. Now this entire part right here has a v in it, so I've got to get it over with the dv. So I divide both sides by that, so I'm going to divide by g minus b over mv on both sides, g minus b over mv. All the way over there. So now this cancels out, leaving me dt equals dv over g minus b over mv. Now this is looking very unfamiliar to you. Why don't you check out back in your notes, lesson 5 from 1D motion. It was the exact same thing, except I didn't have to worry about the forces, so I didn't have this mg in here, and I didn't have this mass here, but it's the exact same concept. Now, I've got dv over, back in lesson 5, it was just v here. That was the only thing I had to deal with, but now I've got all these forces, so I got this other thing. I got the acceleration of gravity minus the drag constant divided by the mass times velocity, and all this stuff looks relatively nasty. I'm going to need something called U substitution. So let me set U, just a letter that we randomly choose to clean this up, to make this nasty part down here not so gross. Let me set U equal to everything in the denominator, G minus B over M V. Well, that's quite nice and nifty because then I can replace everything down here with the letter U. The problem is I have a dv up here as well, and I can't do dv du. Notice the separation of variables idea. I was getting the dv's with all the v's. So dv and u doesn't work. It has to be dv and v. Likewise, it'd have to be du and u's. So if I'm going to put a u down here, I need a du. The way I can get that is by taking the derivative of my equation over here. So I'll do du dv, take the derivative of this equation u, according to v, which is in there. Well, the derivative of the constant g, acceleration of gravity, is a constant, right, 9.81. The derivative of a constant is nothing, so the g just completely goes away. The derivative, that's this part right here, completely goes away. The derivative of this part right here, well, this is v to the first power, right? So this becomes now just minus b over m. That's all I'm left with, minus b over m. Multiply the dv to the other side. du equals negative b over m dv. But I still have one more step that I need to do. I need to get dv. And if you were in class and we did a thing with u substitution, you didn't have to do this last step, but I need to actually do this. I need to get what dv equals, and I got to get this constant out of the way. So I'm going to multiply both sides by the reciprocal. I'm going to multiply by negative m over b. What happens whenever I do that is notice the m cancels here, and the b, the negative, all that cancels. What I do to one side, I have to do to the other, so I have to multiply by negative m over b over here too. What that gives me is negative m over b du equals dv. Now, why is this important? Because I'm trying to get all this grossness going over here with dv's and v's over here. I'm trying to get that out of the way, all this stuff in the denominator. Well, now I have what I need to substitute in. Check this out. I can substitute in down here u, and I know what dv is equal to. I can substitute that stuff in up there. So let's go ahead and do that. So the entire point of u substitution is to make things look a little bit nicer, make it easier to take the integral of both sides. Notice what happened. This entire g minus bv over times v, all that here became u, right? So I put a u down there because of u substitution. Then I took the derivative and solved around to figure out what dv is, because I got to replace dv with something in terms of du. So I took the derivative, solved around, found dv is negative m divided by v du, and I took that and I substituted in right there. Rewrote, purposefully changing colors to try to help you see that. Now this doesn't look as pretty as I'd like right now. Let's get that negative mb out of the way because that's already in the numerator, so I can just move it out. So now I can write dt equals negative m over b times du over u. Now this is much, much prettier, and this becomes a lot easier to integrate now, because whenever I take the integral, and let's slide this over to where I can get at it, whenever I take the integral of t, once again, just like in lesson 5, from 0 to t, and I'm going to take the integral of this du guy, right? And I'm going to end up doing him from v naught, doing that from v naught to v. Now, word of warning. Notice that my endpoints, v naught and v, that's in terms of v, and my integration that I'm about to do is in terms of u. That's okay. We're going to substitute back in here in a second. Now, the derivative on the left-hand side, dt, well, that's just going to be time t, and I'm going to evaluate him from 0 to t, because this is a definite integral. Equals. Notice that I also was able to put the integration sign in between, because this is the only part that I'm actually integrating, because the constant out in front doesn't actually matter. To prove that to you, make this maybe a little bit easier, let me use another example. The integral of 2x to the first is add 1 to my exponent, so now I got x squared, send it to the denominator, so now I have 2 over 2 x squared. But what happens whenever we actually put the 2 outside of the integration sign? Well, you're going to end up with the exact same thing, x to the first, right? This becomes 2 times, now add 1 to that x, so I have x squared, and then send that to the denominator 1/2. 2 times 1/2 x squared is the exact same thing here as 2 over 2x squared. So you can put the integration sign in between without that being any problem, just to make things a little bit nicer. So I have negative m over b, and the integral of du over u, please remember, is ln. So this is going to be times the ln of u. ln of u. And technically I should have used absolute values there, but I'm not going to need that in this problem. And I would be evaluating this between v naught and v. Well, I got a problem here, right? I've got ln of u, and I'm trying to evaluate between v and v naught. That's no good. I've got to get rid of this u. Well, that's not that big of a deal. Whenever I look back up top, I know what u is supposed to equal to. The only reason I substituted u in was try to make this a little bit easier, to get it in something I knew how to do. The integral of du over u, I know how to do that. That's simple. That's ln of u. But this thing, I couldn't do that. But now that I'm back here, I need to substitute back in what u is. All right, in the next step, I'm going to evaluate, plugging in t minus 0, and then plugging in the v for v and v naught, and subtracting those two. All right, so the one confusing thing that I need to point out, that's really not that bad. I plugged in V for V, got that, minus V naught, plug that in here, so that's why the minus sign. This is just like lesson 5 from 1D motion just now with a few other variables thrown in there. Next step, let's actually combine our ln's. Remember, whenever you subtract logarithms, that you are dividing. Now in lesson 5 of 1D motion, it was just V and V naught, but I'm having to deal with forces, so there's a few other things in there now. So let's continue to solve. By the way, quick to point out this, no longer do I have accelerations. The only variable I have, remember V naught's a constant, B, M constant, G constant, B, M, G all constants. The only variable I have is V and T. So now I just need to work a little bit of algebra around here to actually get finally to an equation of velocity depending upon time. Let's get that negative Bm over to the other side first. And notice whenever I did this, I had to either, you could think of it as dividing by negative b over m. Whenever you do that, you're doing the same thing as multiplying by the reciprocal. So I multiplied by the opposite, if you need to think about that. Multiply this by negative b over m. That way the b's cancel and the m's cancel. Let's write that out really fast. So if I multiply by negative b over m, notice the m's would cancel out and the b's would cancel out. And so then you have to put the negative bm on the other side because that's what you're multiplying by. So that's how I came out where I am right now. Next, I have this ln and everything's trapped inside of it. So let's do e to the power, let's take everything e to the power of. All right, so now I've gotten rid of that ln there. Do not get freaked out by the algebraic steps. All you focus on is the next step. I'm trying to get at, remember, this v. I'm trying to get it by itself. Well, I got all this in the denominator, and that's all a constant. So let's multiply both sides by this entire thing right here. Next step I'm going to do here is distribute that actually in. All right, after distributing that, I'm still trying to get at this v right here. I'm trying to get it all by itself. Note, these are all constants besides the time. This is all just a bunch of constants. These are all just a bunch of constants, not a big deal. So now I need to add g to both sides. And excuse me, I said add g. Notice this g is positive, so I have to subtract. So I'm going to subtract g over to the other side. And now I just need to multiply both sides by the reciprocal again over here. Notice I've got negative b over m. So I'm going to need to multiply both sides by negative m over b. And now I want to distribute this in, right? So to all the terms inside there and over to that g. Now check out what happens whenever I distribute this guy in, right? I have a negative times a negative. It becomes a positive here. So I need to make this positive, plus now I have m times m over b times b over m. So these completely cancel out, meaning, negative b over m times negative m over b completely gone. That leaves me with just v naught e to the negative b over mt. Okay, it got a little bit prettier here. It's still pretty nasty, especially whenever I distribute it into the next one. Once again, negative times a negative, negative m over b minus times negative g. That's going to give me a positive mg over b there. That's still relatively nasty, but check it out. Now I've finally gotten it down to what velocity equals. Velocity equals all of this stuff. Now let's see if we can clean this up a little bit, because it kept getting, got grosser and grosser and grosser as we had to unpack the algebra to try to get at this v, which I finally did. But here's an assumption that's generally safe to make. We purposefully did it with v naught, not knowing the initial velocity. What if someone threw the object down? What if someone threw the object up? But most of the time the object is dropped, meaning that v naught is 0 a lot of the time. So what happens if I stick a 0 in here? Well, this entire term goes completely away. Now, getting rid of that middle term sure made things look a little bit better, which, by the way, if you could make that assumption, and I purposefully didn't make it to the end just in case you had to have initial velocity, but if you were told that the initial velocity is 0, you could come all the way back up here, keep going way, way back up to where you actually took the integral all the way up here, and you could have set this guy as 0, which would have made this part right here 0 and would have carried down. You only had a g and things would have been quite a bit cleaner all the way down. But now I'm going to set it as 0. I showed all the way down, so we're good there. Here's another thing. You should recognize from our last slide, from the last thing we did, what mg over b is. Mg over b, according to our last slide, is the terminal velocity. Leading me finally to my final answer, negative terminal velocity times e to the negative b over m times the time, plus the terminal velocity gives me whatever my velocity is at that time. Sometimes you might also see, by the way, people factor out terminal velocity giving you negative e, negative b over m t plus 1. Sometimes you'll see that as well. But that's going to be my final answer, where I work all the way down to that. Now this might require that you kind of dig back through it a couple of times, and that's okay. And we're going to go over it in class again also. And we'll work it through also from the beginning, where v naught is 0. That way it doesn't look as gross and nasty in class. Now go back through this again. This is kind of the only problem. There's one other type of problem that we're going to work also, and it's nowhere close to this bad. So this is kind of the biggest and the baddest thing you've got. And each line of algebra you are capable of doing. You know how to distribute. You know how to multiply things to the other side. You know how to add or subtract things to the other side. You know that how to undo an ln is to use natural e, right? Raise things to the e power. So you know all these steps. It's just a matter of there's a lot of them put together. So go back through this again a few times if need be. We'll talk about it in class, and we'll keep unpacking this.